All right. So again, welcome back, everyone. Welcome back from the Thanksgiving holiday break. I hope you all had a relaxing but maybe productive week as well. I know I did. And like I said, I had a nice 3-hour food coma on Thursday, so that was a very pleasant experience. All right. So, and again, feel free to chat about your adventures from Thanksgiving. That's fine. All right. So I'm going to go ahead and discuss the schedule now. We'll take a couple minutes on that. All right. So it is December. Today is Tuesday, December 1st. So rent check and all that, getting that in, right? Okay, now this week we're going to do chapter 9. All right, we're going to start chapter 9. It's a really good, it's a really good section as a preview for Calc 2. And some of you may have missed this at the end of your intermediate algebra class. Maybe your instructor may not have had enough time to cover that material. But chapter 9 on like discrete math stuff, sequences, series, all that good stuff, and some additional topics. Now remember, chapters 7 through 10, it's a big homework assignment. Chapters 7 through 10, all right, that's that big 250 point, I'll stress that, 250 point homework assignment, big one, all right? And that's going to be due, I've decided it'll be due Monday, December 14th. Okay, so to avoid confusion, both the last 250 point homework assignment covering chapters 7 through 10 and the Alex, those will be due by midnight, Monday, December 14th. So you will have that last weekend. That should be helpful there. Okay. Now you should have gotten your homework grades back for chapters 2 and 3. So you should have all 3 of these up through chapters 2 and 3. Those have been returned by now, emailed. Otherwise, email me if you haven't received that information yet. Of course, I'm still grading these over here. All right. And your last homework due Monday, December 14th. Also, remember that I sent out that link on course evaluations. So if you could fill that out, the course evaluations, the deadline for those, okay, is Friday, December 4th. Okay, so that's some feedback on the course overall. And thank you for filling that out. All right. Now, any questions about the overall schedule? We're not deviating from the syllabus. Any questions about the overall schedule? Okay, we have a lot to do. You can see it's very dense here. It's fun. We're gonna have a lot of fun today. Okay, but it's a lot of stuff too. So feel free to put questions in chat. Also, okay, I'll leave this on the board for a while. Now, I had 3 office hours this past week, and I had a session with a student, I think the Tuesday of the prior week, an after class session where I covered this problem here. You might want to do a screenshot of this or something. It will be on the video, right? I post for the class. But these are problems that I did both after class, like the week before class, this one here, and also all these problems and ideas that I covered during 3 special office hour sessions I had this past week. Okay, so if you want to do a screenshot of that, that's fine. This will also be in the video. And this link here, which I'll send out, this is a GeoGebra link, which will help us out on sequences and series. In fact, I might want to post that right now. Okay, and I'll also email that out. All right, so any questions before we start the videos? Feel free to ask questions in chat. I expect chat to be pretty active today, all right? Any questions so far? Lots of good stuff today. Always good stuff, but especially I have a lot of fun with today, and I have lots of videos. You can see lots of videos. All right, so let's get to it. All right. Okay, let's get to it.
Hi, everyone. Let's start chapter 9 on what I would call discrete math, which is the Math 245 course at Mesa College. The computer science people take that one. Although you're going to see a lot of the stuff in Calculus 2, Math 151, in the context of sequences and series. Calculus tends to deal more with continuous mathematics, where we have y equals f of x and things like that, finding areas and such. And calculus tends to deal more with that kind of continuous mathematics than discrete mathematics. This stuff with sequences and series, it seems like a different part of the calculus sequence. Now, what's the difference? Analogies may help the most. Discrete is digital. Continuous is analog. In other words, discrete is like a dripping faucet. Drip, drip, drip. Continuous is running water. Discrete math tends to deal with things that you can list, even if the list is infinitely long. The idea with continuity is that between two distinct pieces, you may have another piece. It's that kind of idea. All right. Section 9.1 on sequences and series, and section 9.6 on counting principles. I'm using the section numbering from a Larson textbook. Part A, sequences. Now, an infinite sequence can usually be thought of as an ordered list of real numbers. And it is often denoted by either this kind of list or this kind of list. Here in this list, the initial term is a sub 1. Then we have a sub 2, a sub 3, and so forth. Each of these a sub I guys represent real numbers called terms. When I have a sub I here, I is just a generic superscript. I is just a generic subscript. It's not the imaginary unit. It's not the square root of -1. Remember, we keep it real in this last part of the class. But here's a sub 1, a sub 2, a sub 3, a sub 4, and so on. There are infinitely many terms in this infinite sequence. A finite sequence isn't so interesting. Here, in calculus, you often start with a sub 0 or a naught, and then a sub 1, a sub 2, and so forth. That's why I often refer to either the a sub 1 here or the a sub 0 here as the initial term. The first term listed in the sequence. And even then, if someone were to say, what is the first term? This is clearly the first term over here, but someone could legitimately say, well, is this the 0th term? And is this the first term? Well, to avoid the confusion, let's just call this here the initial term for this sequence, and this here the initial term for this sequence. Now, if we're lucky, there's a nice pattern to our sequence of numbers, a pattern that we can describe using simple mathematical expressions. So for example, let's say that you're given this general nth term formula for a sequence. Write the first 3 terms of the sequence with general nth term, a sub n equals n cubed minus 1. Now, this idea is very similar to the idea of f of x equals x cubed minus 1. Again, it's the difference between discrete and continuous. When we had f of x equals x cubed minus 1, you're thinking that snake, right? I hope you are. I hope you remember the snake. Y equals x cubed minus 1, right? A snake that's lowered by 1 unit. And this is a continuous creature here. F is a continuous function of x. And we have this piece of string, right? This snake here. This here is discrete. A sub n equals n cubed minus 1. Now, in both cases here, you're going to plug in. Here, we plug in values for x. Here, we plug in values for n. But here, we can plug in values for x that aren't just integer, 1, 2, 3, and so forth. We can also plug in pi or 1/2 or the square root of 2, right? Whereas here, we only plug in integers. A sub n equals n cubed minus 1, where n is an integer. So it turns out that the graph is going to be a sequence of points, a sequence of dots. So again, this is continuous, this is discrete. Plop, plop, plop. All right. Assume that we begin with n equals 1. And in a pre-calculus class, you normally start with n equals 1. Although again, in calculus, you actually start with n equals 0 quite often. All right, so here n equals 1. This is kind of the flavor of f of 1, sort of. Right? You plug in 1 for n. A sub 1 equals n cubed minus 1 becomes 1 cubed minus 1, and that's 0. So a sub 1 is 0. That's the initial term of the sequence. For n equals 2, a sub 2 equals n equals 2. That's cubed minus 1. Result is 7. Plug in n equals 3. A sub 3 equals 3 cubed minus 1. And that's going to be 26. So the first three terms are 0, 7, and 26. And since we're starting with n equals 1, there's no ambiguity as to what we mean by the first three terms. And again, we can graph terms like so. We can graph terms in the sequence versus n, graph a sub n versus n. So n equals 1, 2, 3 over here. A sub 1 was 0, a sub 2 was 7, a sub 3 was 26. And by the way, you can think of these as beads or pearls along this string. So, and in fact, sometimes in calculus too, when you consider a sequence like this, a sub n equals n cubed minus 1, one strategy that you use sometimes is that you consider the continuous analog of that. F of x equals x cubed minus 1. And the idea is that the beads or pearls here are like beads or pearls on this snake, this string. So all the points here lie on here. And then you can make an argument such as the notion that since this thing approaches infinity as x approaches infinity, then these approach infinity as n approaches infinity. You can talk about properties like those, like long-term properties. Right? Calculus often deals with limits, like long-run limits. All right. No, actually, we won't be doing so much point plotting in this class. I mean, this is pretty rudimentary as far as that goes. Oh, and we sometimes call this the discretization of the graph of y or f of x equals x cubed minus 1. So this is a discretized version of that. Where the domain is not all reals. Here, the domain is assumed to be R, the set of all reals. Here, the domain is the set of positive integers. The domain here is a set 1, 2, 3, and so forth. The domain is a set of positive integers. And in this sense, sequences may be thought of as functions. Functions where the domain is, say, the set of positive integers. And, you know, just like with these guys, we plug in values to get what we want, these values. Next up, sign alternators, which we see a lot of in Calculus 2. Next time.
Okay, questions. Again, this is new for some of you. And by the way, I want to show this link actually. So I'm going to go ahead and click on that link. So here, this is GeoGebra, and you can do things like choose a sequence. You can pick your own, right? Enter your own, right? So you could enter in something like n cubed minus 1, all right? And then let's see, you can drag this slider here, okay, and you can pick up various points. I guess vertical zoom, or go like this. Yeah, because you have to zoom out to the teens, right? You have 70, right? And then zoom out. And you pick up some more points in the sequence. A sub 8 is 511, right? Okay, so you kind of play with GeoGebra. All right, so let's continue on.
Hi, everyone. You may well not have seen these before, but you're going to see these a lot in Calculus 2, Math 151. Sign alternators. Let's say that you have a sequence that alternates between positive and negative, right? Then what pieces will we find? Alternating sequences have terms that alternate, that is, they consistently switch between positive and negative terms. Again, you see them a lot in Calculus 2, like, for example, in series expansions for sine of x or cosine of x. So here's an example. Write the first four terms of the sequence where a sub n equals this over here. -1 all to the n times n. This piece here in blue is a sign alternator. -1 all to the n. Let's see what happens. Again, we assume we begin with n equals 1. So we plug in values for n equals 1, 2, 3, and 4. Okay, here Negative 1 all to the first is negative 1 times 1, we get negative 1. So take a look here. Okay, so the n here stays positive. We're only plugging in positive integers. The n here stays positive. The sign alternator over here tells you what sign you get. Is it going to be positive or negative? So if negative 1 is raised to an odd exponent, the resulting term will be negative. I'm assuming that these other pieces are positive in value. And in calculus 2, you typically separate it out, so that is the case. Over here, we have negative 1 to the second power. Anytime you have an even exponent, you end up with a positive, right? So we know, so the sign alternators here tell us that we alternate between negative, we start with negative, positive, negative, positive, and so forth. So we get negative 1, positive 2, negative 3, positive 4, and so forth. So recall that the parity of an integer is either even or odd. The parity of n here as an exponent determines the sign of the overall term. So the exponent is really key, right? With the sign alternator alone, all right, when negative 1 is raised to an odd exponent, you get a negative. When negative 1 is raised to an even exponent, you get a positive, assuming these other pieces are positive. So what,
by the way, that means it'd be the absolute values, by the way.
do we do if we want to go and change these to positive, negative, positive, negative, assuming the same absolute values, these guys over here? So what do we do to get from here to here? Well, basically, if I give you something that's negative, what do you multiply by to flip it over to positive in such a way that you have the same absolute value, which is the n here? You could multiply by negative 1. Multiply by negative 1. Right? Well, what happens when you multiply negative 1 all to the n by negative 1 to the first? When you multiply powers of negative 1, let's say, you add the exponents. So we can use negative 1 all to the n plus 1 all times n. So for example, when n is 1, right? Let's see here. I'll put this in, let's see here. Put this in green. All right. So here we have the signs for negative 1 all to the n. Over here, we have negative 1. Oh, okay, I'll erase this stuff. Over here, we have negative 1 all to the n plus 1. So these are the signs if we have negative 1 all to the n. These are the signs if we have negative 1 all to the n plus 1. So if n equals 1, exponent here is odd, we get a negative. But if n equals 1, then 1 plus 1 is 2. Negative 1 all squared, that gives a positive 1. Okay? But here's the bottom line. When n equals 1, if this exponent is odd, we get negative. If this exponent is even, we get positive. But wait a minute. When n plus 1 is even, what else is even? N minus 1. We can subtract 2, right? In other words, if n is odd, how do we switch parity? We can add 1 to the exponent, or we can subtract 1 also. So this would also work, and we get the same sequence. We get the same sequence as this one over here, where we take these terms and we basically flip all the signs. So we get positive 1, negative 2, positive 3, negative 4. It's this other sign pattern here. In fact, there are infinitely many possibilities. So to get this pattern over here, we could use n plus 1, n minus 1. We could use n minus 3. You can keep subtracting or adding by 2, right? how do you get a bunch of numbers with the same parity? You can add by 2 or subtract by 2 any number of times. Okay, n minus 3, n minus 5, and so forth, n plus 3, n minus 5, those would work. For these guys here, -1 to the n, what else would work? Well, whoops. What else would work? Well, instead of n, we could have n plus 2, n plus 4, n plus 6, n plus 8, or n minus 2, n minus 4, n minus 6. If you take an exponent and if you add to or subtract to any integer number of times, then you'll have the same parity. And the parity of the exponent on the -1 will tell you what sign pattern you get. Speaking of even versus odd, if n sweeps out over all the integers, then 2n sweeps out over all the even integers. That's good to know. So if n equals 1, this is 2. If n equals 2, this is 4, and so forth. So, okay, so here's n. In fact, I'll do it this way. N equals 0. Well, no, so let's start with n equals 1, 2, 3, 4, and so forth. Okay? This wants to deal with 2n. So 2n, we double n to get 2n. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. Now, how do we get to, so this sweeps through even integers, all right? In this case, positive even integers. We're focusing on positive even integers here. Now, how do we get from here to, let's say, positive odd integers? How do we get to 1, 3, 5, 7? Okay, well, let me ask you, how do we get from 2 to 1, 4 to 3, 6 to 5, 8 to 7, and so forth? What do we do to 2n to get these values over here? We subtract 1. 2n minus 1. All right. 2n minus 1 will sweep over odd integers, also 2n plus 1. Now, if you start with n equals 0, then to get 1 as your first term, your initial term, you need to use the 2n plus 1 form. If n is sweeping out over all the integers, then it doesn't matter. These will both sweep out over all the odd integers. All right. So next up, factorials and counting. Next time.
All right. Any questions before we go on? Any questions? Because you see this stuff all the time in Calc 2 and higher math. Any questions? Okay, factorials may be familiar to you.
Hi, everyone. So let's talk about factorials. Do you see the n factorial button on your calculator? On some TI calculators, you might need to look under the PRB or probability menu, and you may see an exclamation point. N factorial, not n excited or n yelling, n factorial, right? And it's often used to describe sequences as part of formulas for sequences or series. For example, in the series expansions for sine of x and cosine of x, you'll use factorials in the denominators. All right. Now we define 0 factorial to be 1. That makes everything work out. If n is a positive integer, if n is in the set z plus, then n factorial is the product of the integers from 1 to n. So if n is big enough, then you can do the whole ... thing here, right? You can do a count up. N factorial is 1 times 2 times 3 times times n, or count down. N factorial, you can start with n, and then subtract by 1 each time, n minus 1, n minus 2, and so on, down to 2 and 1, basically reversing this list of factors. And here, 2 here, 1 here. All right. Examples. 0 factorial is 1, remember? That makes the formulas consistent in this section. 1 factorial is 1. 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. 4 factorial is 4 times 3 times 2 times 1, or 24. Now take a look here. From 1 factorial to 2 factorial, we multiply in the 2. From 2 factorial to 3 factorial, we multiply in the 3. And guess what? To get from 3 factorial to 4 factorial, to get from 3 factorial to 4 factorial, you multiply in the 4. All right. And that's going to be a recursive way of developing the list of factorials. We'll talk more about recursion later on. Okay, so what if we wanted 5 factorial? Well, yeah, it is 5 times the rest of this. Okay, that's exactly the point. It's 5 times all of this, right? It's 5 times all of this. So it's going to be 5 times 4 factorial. Okay, 4, it just says 4 factorial is 4 times 3 factorial. 5 factorial is 5 times 4 factorial. Basically, you bring in the next integer to get the next factorial. Factorial is at the same level of as exponentiation in the order of operations, in the sense that they both represent successive multiplications. So, you know, 2 cubed, right, is 2 times 2 times 2, right? Whereas something like 3 factorial would be 3 times 2 times 1. They represent successive multiplications, and they're each at the same level on the order of operations in terms of the order you work an expression out. All right, so the factorial binds more tightly than the multiplication operator. That's why here I can write 4 factorial equals 4 dot, or multiplied by 3 factorial, right? Because even in the absence of grouping symbols, it's automatically assumed that the 3 factorial binds tightly, right? Then you multiply in the 4. Still, if this makes you feel more comfortable, be my guest. Speaking of the recursive definition of the factorial function, remember 0 factorial is 1. And then to get the new factorial, n factorial, you take the previous factorial, n minus 1 all factorial, and multiply by n. Like here, this is the case where n equals 4. To get 4 factorial, you take the old factorial, bring in the new number. Again, to get n factorial, take the old factorial, bring in the new number, the new integer. Again, this is called a recursive definition of the factorial function because it describes how previous values determine later values. Okay, it's like climbing a ladder. All right. Next time, we're going to apply factorials to counting. I know how to count. Are you sure? If you've taken Math 119 statistics, maybe, but counting is harder than you think. Next.
Okay, any questions? I was reintroducing factorial. Oh yeah, of course, multiplying by 1 doesn't do anything, but it's good to see that pattern, right? Yes, of course. So, 3 factorial, of course, can be written as 3 times 2, but the times 1, that's just kind of a reminder how the countdown works. Sure. Right, yeah, but right, multiplying by 1, that doesn't do much. That's right. Okay, any other questions about factorial before we go on to counting? Okay, and there's lots of stuff on my Math 119 side, actually. All right, any questions? Let's relearn how to count Math 119 style. All right,
it's time. Hi, everyone. We're going to talk more about factorials and how they relate to principles of counting. You think you know how to count? Well, if you did well in our Math 119 statistics class, perhaps. We'll see. And also, simplifying factorials will be a key issue in calculus 2. Math 151, when you're manipulating things like series. All right. Example, how many ways are there to order a standard deck of 52 cards? So imagine a deck of 52 cards, a random deck lying on the table. So it's not freshly opened, right? So how—
You know what? I'm gonna go ahead and be cute here. I'm gonna throw in my videos right now, okay? Because I have some videos about cards. All right, let's go back to counting card orders.
How many ways are there for the deck of 52 cards to be ordered? These are called permutations. Or total permutations, since we're going to order all the cards, as opposed to partial permutations, where you just take and order some of them. We're going to order all 52 cards. Now, as you put the 52 cards on the table one by one, how many possibilities are there for the first card? Well, there are 52 cards, 52. We do not put this card back in the deck. How many cards are left for the second card you put down? How many possibilities are there left? Well, you've taken one card out. Whatever it is, you have 51 cards remaining that this card could be. Then, after these two cards are placed, whatever they are, how many possibilities are there for the third card? There are 50. I could go on and on, but I don't want to waste your money as a student. Eventually, you only have two cards left, right? Okay, and there are two possible. At one point down the line, there are two possibilities left for this card. And then after you put down that second to last card, how many possibilities are there for the last card? Well, there should be only one card left in your hand, and it goes there. Now, for each of these 52 possibilities for the first card, there are 51 possibilities for the second card. Imagine a big, bushy possibility tree. So there are 52 branches in this first round on the possibility tree. For each of these branches, there are 51 possibilities for the second branch, the second card, and so forth. Big, bushy tree. How many total paths are there along this big, bushy tree? It's going to be 52 times 51 times 50 times times 2 times 1. That's going to be 52 what? 52 factorial. By the countdown scheme over here, remember, n factorial is the product of the integers from 1 to n. Or if you think of it as a countdown from n to 1. And I was looking at 52 factorial more in terms of the countdown. 52 factorial equals 52 times 51 times 50 times times 4 times 3 times 2 times 1. That's 52 factorial. Again, 52 possibilities for the first card, then 51 for the second card, then 50 for the third card, and so forth. So the number of ways that you can order the deck is 52 factorial, which, if you work it out, is about 8 times 10 to the 67th. That's an 8 followed by 67 digits, which is literally astronomical. Let's take a look at it. This is Mathematica, the big brother of Wolfram Alpha. Okay, let's work out 100 factorial. Now, I want to make a point. I'm sorry, we're going to do 52 factorial first. Let's do 52 factorial first. Now, I want to make a point here. Well, up here, when we first described and listed some factorials, look at this. It started off slowly and low, 1, 1, 2, 6, 24. This is going to be 120, it turns out that factorials grow fast. In fact, they grow faster than any exponential function, any fairly basic exponential function, because with a fairly basic exponential function, for example, 2 to the x, or 2 to the n, let's say, the discretized version, you're multiplying by the same number over and over again. Here, you're multiplying by bigger and bigger numbers. So n factorial grows even faster than 2 to the n, or 3 to the n, or in the long run, even something like 1,000 to the n. In the long run, point is, factorial grows very fast, eventually faster than any basic exponential. What is 52 factorial? It's massive, it's astronomical. Again, look at this. 52 factorial is this gigantic number. In scientific notation, it's more than 8 times 10 to the 67th, an astronomical number.
That gets cut off.
Now, on your calculator, again, n factorial grows in value very fast as n grows. Many calculators can't even handle 100 factorial. I doubt yours can. I'll give you a moment. Get that calculator out. Try to get 100 factorial. Odds are you're going to get something like error or overflow. I would bet your calculator can't even handle it. Mathematica can. Let's try 100 factorial. Well, if you thought this was big, get a load of this. Wow, it takes a couple of lines here. I'll blow it up a bit. Oh, wow. Makes this look almost puny. Scientific notation. It's over 9 times 10 to the 157th. So we're talking over.
Yeah, I tried to blow it up on my Mac, but the blowups doesn't work on Zoom. You do catch the scientific notation just a moment.
A number where you have a 9 followed by 157 zeros. This number is a 9 followed by 157 digits, in fact. Why do we have a bunch of zeros over here? These are actually zeros. This isn't rounding. Why are there a bunch of zeros here? Well, one reason why is that we know that we're multiplying by numbers like 10 and 20 and 30, but even something like a 2 times a 5 will give a 10, right? So there are a bunch of integers in here that'll multiply to a multiple of 10. These are massive numbers, beyond astronomical.
Yeah, okay, there we go. So there you see the full exponential form. It's about 9.3 times 10 to the 157th. Most calculators can't get beyond a Google, 10 to the 100th. That's called a Google. I think because the little kid called it a Google. All right.
In fact, if we were to Google, hey, let's just Google. Google, let me ask you something, Google. Let me ask you something. How many atoms are there in the universe? Okay, it is estimated that there are between 10 to the 70th, 10 to the 78th, and 10 to the 82nd atoms. So maybe about 10 to the 80th atoms. There are about 10 to the 80th atoms in the universe, which is bigger than 52 factorial, but 100 factorial dwarfs that. In fact, this is on the level of like about the square of that. This is more like the square of that. It's ridiculous. All right. But in general, let's get back to the combinatorial interpretation. The number of ways to order n distinct items, the different possible orders called permutations, the number of total permutations of n distinct items is n factorial. When I say distinct, I mean no clones. So for example, I don't allow things like sort of copies of cards, for example. I don't allow. The items must be distinct. Otherwise, you have problems. If you have clones, right? Okay, although they can be managed at some level. Okay. Now, let's talk about another example involving a deck of cards, but this time we have a different idea going here.
All right, any questions before we go on? I wanted to discuss how explosive factorials can be. In the long run, they grow faster than any exponential function, really. Questions? Poker. 5-card stud. Let's talk about that.
Hi, everyone. Let's say that you fly to Vegas. I have a few times. And let's say you land in Vegas and you go to McCarran Airport. As soon as you get off the plane, what do you see? What do you see? You see slot machines, video poker machines right there at the airport, including video poker machines, right? Where a machine will randomly, we think randomly, will give you 5 cards, right, from a deck of 52 electronically. So assuming that there is true randomness here, right? There's no rigging. How many possible hands of 5 cards can be drawn from a deck of 52 cards? In other words, how many ways are there to choose, or really how many ways are there for the computer to choose 5 cards from a deck of 52? So imagine these 5 cards selected by the computer. How many ways for the computer to pick these cards? Now, I want to ask you something. Let's say that the video poker machine spits out a 10 of hearts, an ace of hearts, a king of hearts, a queen of hearts, and a jack of hearts. If you know poker and you see a hand like this given to you by a machine, how should you feel? You should feel very, very happy, especially if you put in a lot of money. Why? Because this is the best hand. It's a royal flush, right? Now, is anyone going to say, oh, I feel kind of sad because the 10 of hearts was the first card. It should be last. Well, no, because you have the right to sort of mentally move the cards around. The order among the 5 chosen cards does not matter. So this thing is a royal flush, regardless of the order that these 5 cards are in, right? The order among the 5 chosen cards does not matter. If you see something like this, you're thrilled. Okay, I mean, at the very least, you'd have a flush anyway, but in fact, you have a royal flush. The 10 of hearts, you're allowed to move this around. If you can imagine 5 cards in your hand, you have the right to reorder the 5 cards in your hand any way you want. So order does not matter among the chosen cards, right? There are 5 winning cards, right? I think of them as winning cards. There are 5 winning cards. These are the 5 chosen cards, all right? And we don't care about their order. Ignore the order among the chosen cards. Now, if there are 5 winning cards, then there are 47 losing cards. 52 minus 5 is 47. If 5 cards have been chosen, 47 cards have not been chosen. And of course, we don't care about their order, bearing in mind that we're not concerned about issues of trading yet, okay? So assuming that we're not concerned about the issue of card trading yet, we don't care about the order among the 47 losers. The bottom line is these cards were not among the 5 chosen cards. So we ignore the order among these as well. If you imagine the old cartoons, the old Alice in Wonderland cartoons, where you had living cards running around, imagine the 52 cards running in a marathon, okay? And let's say that the first 5 cards that cross the finish line are all winners, but they all get the same trophy. They all get the same trophy. It's not like the Olympics where it's gold, silver, bronze. They all get the same trophy. So if you finish 5th, that's just as good as finishing 1st as far as your reward goes, right? Okay. And likewise over here, if you're a loser, you're a loser. We're very Darwinian. If you're a loser, you're a loser. If you finish 6th, you may as well have finished last, number 52. The order among these cards does not matter. Now, of course, it does matter if you're card number 5 versus card number 6. That's a huge difference, right? Okay, because that crosses this dividing line. But between 1 and 5, no. Between 6 and 52, no. Right? Between 5 and 6, yes. Okay. Another way of looking at this, imagine that you have a Halloween bowl with candies in it, 52 different candies in it. 5 kids, or how about this? One kid comes to your place and you decide to give the kid 5 candies. All right, you decide to give the kid 5 candies. Now, don't worry about smushing things or anything. How many ways are there to grab 5 candies from your bowl where no one cares about the order? Okay, so it doesn't matter which of the candies is first, which is fifth. Okay, these are like the 5 candies in your hand that you're going to give the kid, and it doesn't matter what order they're in. Here are the 47 candies left in the bowl, and no one cares about their order, right? All right. So what is the number of ways? How many ways are there to choose 5 cards from a deck of 52? This number is denoted by 52C5 combinations, the number of combinations of 52 distinct items, taken 5 at a time. Again, no clones. And you're not allowed to take the same thing out twice. Once you're chosen, you're chosen. Or it's also known as 52 choose 5. Among the 52 distinct items, how many ways are there to choose 5? Where you don't care about order among the 5 or among the losers. All right, here's the formula. Now, you can actually calculate this directly on a scientific calculator. On the TI calculators, you would use the PRB probability menu again, and you'll see the NCR function. It's a function of these two things, N and R. N is the total number of items. R is the number of items you pick or choose. Now, you may be able to calculate this directly in your calculator, but I would like to show you the formula, and the skill of simplifying this is actually relevant on the homework and maybe the final. So I do want to talk about this formula. Not that you have to figure out its structure, but how to simplify this, because that skill of simplifying will be important in Calc 2. First of all, I would like to explain, not that you have to know this, but it's cool to understand. Why does the formula look like this? Incidentally, this number is also referred to as a binomial coefficient, because we're going to see this in the binomial theorem later on in chapter 9. And also it's related to the binomial distribution in probability and statistics. Okay, now why does the formula look like this? The 52 factorial, what does that represent? The 52 factorial, what does that represent? The 52 factorial represents the number of total permutations of the 52 cards. So imagine doing what we did before, right? In the previous example, where we took the 52 cards in the deck and we put them down on the table one by one in order, from first to last, in some random order. It's not a brand new deck of cards. Okay, so same thing up here, okay? Consider that. But wait a minute. Imagine these are the 52 cards. We don't care about the order among the 5 chosen cards. How many ways are there to order these 5 cards? 5 factorial, or 120. So we can divide by 5 factorial. We divide by 5 factorial because we do not care about the order among the 5 cards. So we divide by 5 factorial, or 120. If you're still not sure why that is, don't worry about it, but that's the basic idea. It's because we don't care about their order. And likewise, of course, we don't care about the 47 losers, so we can
Their order.
divide by the 47 factorial as well. That's huge. The fact we don't care about the order among the losers, that's really going to reduce this number down, all right? Okay, so we divide by 47 factorial because likewise, we do not care about the order among the 47 losers. Although, of course, if you're still drawing cards, like if you're allowed to trade cards, right? You're playing poker with more than 5 cards, then yeah, sometimes in poker you care. Okay, but if you're just given these 5 cards and there's no trading allowed, that's it. Okay. And by the way, this is a double division. A lot of people forget that. It's a double division. In fact, many people, this happens in chapter 0. When people divide something by like 7 pi or something, people forget it's a double division and they mess up the calculation. The 52 factorial here is divided by both the 5 factorial and the 47 factorial. It's a double division. Don't just go this divided by this times that. That doesn't work. It's a double division. If you do times, you have to use grouping symbols down here. So be careful. A lot of people miscalculate this and also this. So it may be safest to find this on your calculator directly. Okay, so how can we simplify this? How can we simplify this? So here's the idea. And this is, again, this is something you're going to see in Calc 2, key skill. Math 151, Calc 2, key skill. Simplifying factorial expressions. That's a key skill. And a lot of people enter Calc 2 forgetting this stuff or not knowing it. Okay, so here's the idea. In the numerator, how can we think of 52 factorial? Well, using the countdown idea, it's 52 times 51 times 50 times 49 times 48 times, wait, what's it going to be? It's going to be 47 times all the way down to 1. Wait, what is that? That's 47 what? When you multiply all the integers from 47 down to 1. That's going to be, remember, 47 factorial. On the bottom, we have 5 factorial, which is 120. You might remember that. That's a good thing to remember, by the way, is 120. And then, hey, look at this, 47 factorial. Now, 47 factorial is a big number, right? 47 factorial is a big number, but we don't care what it is because whatever the heck it is, it's going to divide out, right? The 47 factorial up here divides out with a 47 factorial down there. And that's a huge relief. We don't have to mess with that massive number because it divides itself out. And then look at this. A basic $2 calculator should be able to figure this thing out, right? A calculator from like 60 years ago should be able to figure this thing out, right? Okay, all this here. All this here. Well, let me do it better. Okay, all of this here. All this. A basic $2 calculator can figure this out. What is it? Give you a moment. So you could either do 52C5 on your calculator, right? 52C5 on your calculator, if you figured it out by now, or work this out and you get Oh, and let's remember, up here, why did I stop at 47 factorial? Because its twin was down here. So a general strategy is to unravel kind of like the bigger factorial until the point where you can cancel with the other factorials in the problem. All right, so this is what we did. This is a copy of what we did here. All right, and we get about 2.6 million. I used to have this memorized when I taught stats a lot. I used to have this memorized. 2,598,960. After some of the numbers I've shown you, like 52 factorial and 100 factorial, this almost doesn't seem like much, does it? Remember, in dollars, I'd like to have this amount of money, sure. Pretty big. Oh, and by the way, I worked this out one time. Now, of course, it helps a lot to know some statistics. There's a book by Edward Packel, which covers this topic of probability and gambling. Edward Packel has written books on probability and gambling. Check that out. It turns out there's about a 50-50 chance of getting at least a pair. And you're a bit, I'm trying to think, I think you're a bit more likely to not get something than to get something, I think. Yeah, but it's about a 50-50 chance of getting at least a pair in poker. A pair is like the lowest hand that's meaningful. After that's high card. All right. Now, By the way, we're guaranteed to get an integer always. That's a number theory issue. This might surprise you, but this kind of structure will always give us an integer if it's like that. Now, in general, assuming that n and r are reasonable values, right? They have to be non-negative and all that, integer. The number of ways to choose r distinct items from a set of n distinct items, if the order among the chosen items is irrelevant, okay, is given by NCR. That's combinations, remember. The combinations of n items taken r at a time, or n choose r, which is given by n factorial, the total number of total permutations, and you divide by r factorial, because you don't care about the order among the r winners, and you divide by n minus r all factorial, because you don't care about the n minus r losers. Again, these are called binomial coefficients. We'll see why in section 9.5. Again, try to find this button on your calculator. You might save yourself some heartache. Although the problem that we talked about earlier, see, this whole notion of canceling factorials, unraveling and canceling, that issue is going to help you on the homework and on exams. Although I'm going to be kind of mean. Well, not in the sense I'm going to prepare you for calculus, but you're going to use expressions in things like n and k, not just these constants here. Same basic principles, but it looks freakier. Try the homework. You have to practice the homework, absolutely. It'll be fun. You'll be prepared for calculus 2. Because let me tell you something. When I used to teach calculus 2, a lot of students had no idea what was going on here, even with just numbers, let alone these things. All right. By the way, if you thought this was a big number, right? What if we cared about the order among the 5 chosen cards? That's the next topic, right? Yeah, that's NPR, 52P5. If we care about the order of the 5 chosen cards, okay, then the number we want is 52P5, partial permutations. The number of partial permutations of 52 distinct items taken 5 at a time. This will not be on your homework or on exams in this sense, although bear in mind that NPN is n factorial. That's the number of total permutations of n items. That, of course, is totally fair, but NPR more broadly, I won't be pushing. So let's say we care about the order among the 5 chosen cards, right? Then here's the deal. If we care about the order, then one way to look at it is that we don't divide by the 5 factorial there because we care about the order. 5 factorial is 120. So this number is going to be 120 times as big, right? Because before we divided by the 120. Now we're not. This number is going to be 120 times as big as the 2.6 million or so I got earlier. This is almost 312 million. Many, many more possibilities. Because let's say that you're playing lotto, right, with these lottery tickets and you wait for those lottery balls. It's going to be a lot harder to win probability-wise if the order among the balls actually mattered. Normally they don't. Normally that's a C problem also. Okay. Oh, and another way you could have looked at it, right? What we did early on, right? How many possibilities are there for the first card? 52, right? Imagine the 5 winning cards like we did here, right? The 5 cards from Alice in Wonderland running in the marathon. Okay. We want to know the 5 winners over here. But this time is like the Olympics, where we give different medals: gold, silver, bronze, tin, spit, I don't know, dirt. Okay, anyway. And these people get participation trophies. I don't know. All right. Anyway, okay, 52 possibilities for the first winner, the gold medal winner, 51 possibilities for silver, 50 for bronze, 49 for tin, 48 for spit or dirt. Okay. Right, and that is that. All right, folks. We've done lots of counting so far. So you thought you knew counting? Yeah, this is a lot, right? You got to think about it. Next up, we're going to talk about recursively defined sequences. And remember a function of n, an operation where we've already defined recursively. Next time.
By the way, I did mention the connection with probability earlier in the video, right? Was the probability that that you get such and such happening? It's 1 over the number of possibilities, right? Okay, like what's the probability that you get a particular 5-card hand is about 1 in 2.6 million, right? So this is one of my favorite videos. This is a very famous video. These kinds of calculations are meant to show how unlikely it is to win a lottery, right? With the winning the 5 balls and all, with the 5 balls and all that. Again, going back here, it was the 2.6 million, 25. Yeah. It was the about 2.6 million here.
To a lot of students, we cared about the order among.
So yeah, there are 2.6 million possible 5-card hands, right? And if you consider the issue of the royal flushes, I'm trying to find my royal flushes. So there are about 2.6 million possible hands, and the probability of getting any particular hand is 1 over that.
Because we do not.
Here we go.
Cares about their.
So the probability of getting this particular hand in any order, right, is 1 in about 2.6 million, right? Now there are 4 royal flushes, right? Hearts, clubs, spades, and diamonds. So the probability of getting a royal flush, any suit, is 4 over the 2.6 million or so, and you can reduce that. So this is related to probability. All right. Any questions before we go on? Because we're going to talk about more about sequences. Any questions? All right.
A function of n, an operation where we've already defined recursively. Next time. Hi, everyone. Before, we've been talking about things like a sub n equals, well, what, remember -1 to the n times n or something like that, right? Kind of like a function of n. This was a closed form formula. Or you can find a sub a million, right? Plug in a million and you get positive a million. This is a closed form formula. Now, sometimes sequences are defined recursively. We saw that before. You can think of the factorial sequence. A sub n equals n factorial. Where you can actually start with n equals 0, actually. 0 factorial equals 1, and then n factorial. To get this factorial, you take the previous factorial, n minus 1 all factoria, and multiply by the new number. Remember, and you can plug in some small positive integers to look at some examples. What's 4 factorial, right? It's 4 times 3 times 2 times 1. Wait a minute. What is 3 times 2 times 1? What is 3 times 2 times 1? It's 3 factorial. So this is an application of this where n equals 4, but this applies to any positive integer n. Recursive definition. You can go from 0, well, as we've said before, you can go from 0 factorial to 1 factorial, to 2 factorial, to 3 factorial, to 4 factorial. Okay, here from 1 factorial to 2 factorial, you multiply by 2, and then you multiply by 3 to get 3 factorial, then you multiply by 4 to get 4 factorial, multiply by 5 to get 5 factorial, and so forth. So you're building up the sequence instead of just plugging in a number. Now, the problem with this, though, is that if you just have a recursive definition, it could take you a really long time to get to a sub 100, for example. Whereas if you had a closed form formula, it'll be a lot easier if the formula is reasonable. All right. So recursive definitions, it might be okay for the first few terms, but then for a sub 100 or a sub 1,000, you may have some problems. So hopefully we can get a closed form if possible. All right. Now, the most famous recursively defined sequence is a bit more complex, actually. All right. Here's a good Facebook problem, right? What's the next number in the sequence? 1, 1, 2, 3, 5, 8, 11.
That should be 13.
Wait, I'm sorry. It's 13. Can't add. Okay. Well, what's the pattern? I kind of gave it away with my mistake. What's the next number? I kind of gave it away with my mistake. 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 5 is 8. 8 plus 5 is 13. And 8 plus 13, that's going to be 21.
I forgot 2 plus 3 is 5,
And
of course.
on.
Yeah.
So our seeds, we have 2 seeds. We start with 2 ones. And then you keep, to get the next number in the sequence, you add the 2 previous numbers. The Fibonacci sequence, very famous. This is probably the most famous recursively defined sequence. Now, there is a closed form formula for this, right? There is a closed form formula. No, and by the way, okay. There is a closed form formula, and it's like this. A sub n equals this horrendous looking thing, which you actually work out in a discrete math class, actually. Now, of course, you don't have to do anything with this. I'm just saying, even this thing, which doesn't seem like it has a nice closed form formula, well, maybe it doesn't. It has this. It's not that nice, but it does have this. Okay, but this is one thing you try to do in higher math classes. Given a recursively defined sequence, find a closed form formula. Right. And there are many sources on the Fibonacci numbers. So if you want to find a sub 1,000, I guess you'll have to plug it into this formula. It'll take a long time to do it here. Now here's a simpler recursive sequence. Consider the sequence defined recursively by a sub 1 equals 10, and a sub k plus 1 equals twice a sub k, where k is a positive integer. Wait, what does this mean? This means that the initial term, a sub 1, is 10. Well, you got that, okay? Yeah, the first number is 10. I think we got that. But what is this saying? This is saying that every time you want the new number in the sequence, you take the number you're currently at and you multiply by 2. Find the first 3 terms of the sequence. Go. Well, basically you're doubling. You're doubling the current term to get the next term. When you double 10, you get 20. When you double 20, you get 40. Now, if you want to do it more brute force, a sub 1 is 10. A sub 2, if k equals 1, remember k could be any positive integer. If k is 1, then k plus 1 is 2. All right. A sub 2 is twice a sub 1. 2 times 10 is 20. So you could do it this way, more brute force. All right. And for a sub 3, okay, it's twice a sub 2. It's twice the 20 here. So you get 40. So you could use this very directly, or you could look at this and go, is there a basic way I can say how I can get from one term to the next? In this case, you take the current term and double it to get the next term. Now, if your formula here is more complicated, then you're going to have to pretty much plug in. Okay. Next up, summation or sigma notation. And before we do that, I want to go back here and show you the recursive definition for this thing. So here, a sub 1 is 1. A sub 2 is 1. These are our 2 seeds. And then, And then A sub K equals A sub K minus 1 plus A sub K minus 2. Where K could be 3, 4, 5, and so forth. Integers greater than or equal to 3. All right. And that would be the recursive definition. Basically, I'm saying that, let's say we want to find out what the kth term in the sequence is, okay? To do that, we have to add the two previous terms. You have to add dad and grandpa, or mom and grandma. So to get the kth term, you have to add mom and grandma. To get the kth term, you need to add the k minus 1 term and the k minus 2 term. These indices correspond to the order number in here. Here's okay, as far as k goes, well, k is 1 here, k is 2 here, k is 3 here. That's the first one where you can apply this, and so forth. All right. Oh, and also, I forgot my Olympics joke way back here before we get to the summation sigma notation. Remember the Olympics? All right, in China, seriously, if you're a Chinese Olympian, if you come in second, you may as well have come in last. If you're a Chinese Olympian from China, you got to come in first. If you're not a gold winner, you're a loser. It's very, very awful. Okay, next time, summation or sigma notation.
Well, it's time for a break, but before we get to a break, I want to show you something as we enter the break about starting. All right, let's restart.
Hi, everyone. I can't leave the Fibonacci numbers without mentioning its surprising applications in nature. Sunflower petals, numbers of petals, pine cone and seashell patterns. If there's time, I hope to be able to email out a link to Art Benjamin's TED Talk on the Fibonacci sequence. It's fascinating. All right, off to summation or sigma notation. We're taking the leap to series. All right. So basically, this symbol here is the uppercase Greek letter sigma. If you've taken statistics, you remember his little brother. Lowercase sigma stands for standard deviation, a measure of spread in data. The big brother, uppercase sigma, stands for summation. It's a summation operator. So we use it to efficiently indicate the addition of terms. We take the sum of terms in a sequence. And that's why this stuff's here, because we often add up terms in a sequence. So for example, evaluate the following finite sum. All right, in calculus, we care more about infinite sums, but for right now, let's get started with finite sums and get used to this notation. I here is the index of summation. It's the counter for the terms, right? We start with, I use k or n before. We use I also. I could equal 1, 2, 3, or so forth, right? Here, actually, we start with I equals 0, actually, come to think of it. Here we start with I equals 0. I mean, if you can't see this, I could be 0, 1, 2, 3, and so forth. In fact, you'll find that in like differential equations, you can get negative numbers. All right, anyway, so we're going to consider a sub 0, actually. A sub 0, in a way, is our initial term that we're considering, right? I here is the index of summation. Sometimes j is used, k is used, n could be used, but I here does not mean the imaginary unit. Remember, we're keeping things real. So we can think of I as a dummy variable in the sense that it's like it's like your new coworker. If you replace one dummy with another, nothing never ever changes, right? If you replace I with J, K, N, whatever, you're going to get the same result. If you replace one dummy with another, nothing ever changes. Some people say that about politicians. All right. So summation, I equals 0. That's the lower limit of summation, the 0 here. In pre-calculus, you often start with 1, but I'm being cute here. I'm starting with 0. And remember, in calculus, you often start with 0. 3 here is the upper limit of summation. And in fact, I'm going to take away the ... Basically, I'm indicating that we're going to want to plug in all the integers from I equals 0 to I equals 3. So I'm eventually going to plug in each of these values of I into this expression here. Here, a sub I equals 5i squared minus 1. So what we're going to do is we're going to successively plug in 0 to get a sub 0, 1 to get a sub 1, 2 to get a sub 2, 3 to get a sub 3, and do what with the results? Add them using the summation operator. All right. So always, whenever you see this, summation I equals 0 to 3 of a sub I, it always, always, always means this. A sub 0 plus a sub 1 plus a sub 2 plus a sub 3. Again, you're plugging in the integers from 0 to 3, one by one, and then you're adding the results. So when you plug in these values for I, when you evaluate a sub 0, and a sub 1, and a sub 2, and a sub 3, okay? Remember, it was 5i squared minus 1. Here we have 5 times 0 squared minus 1, 5 times 1 squared minus 1, 5 times 2 squared minus 1, 5 times 3 squared minus 1. Remember, you're adding these, okay? So if you want partial credit on something, make sure you put these plus symbols. In fact, I think it's a good idea to at least show this work. I realize that this is a lot of writing, and in fact, I don't require you to write this out on homework or exams. However, I do expect you to write this, okay? You should work out what these terms are, indicate the summation, indicate the plus signs, right? Okay, and of course, give the final answer. A sub 0 is -1, a sub 1 is 4, a sub 2 is 19, a sub 3 is 44. In some cases, there are certain cancellations you can exploit where you can be cute, but it's usually most straightforward to work out these terms individually, okay, and then add them all up. The sum of these is 66. So we've evaluated the sum. Now this is a finite sum where we get used to the notation. What happens if we add up infinitely many terms? Okay, now just in general, a series arises when we take the sum of terms of a sequence. So kind of like what we did before, except here I'm starting with 1, and I'm changing the index to k. That's fine. Here's an example of a finite series. You see this a lot. Summation from k equals 1 to n of a sub k, which is a sub 1 plus a sub 2. I'm assuming n is kind of big. A sub 1 plus a sub 2 plus a sub 3 plus yada, 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 plus a sub n. I assume that n is a positive integer. This is an example of a finite series. And in fact, later on, we're going to call this S sub n, the nth partial sum. This is going to be the nth partial sum, which is the cumulative sum, kind of like the running total, of the first n terms of a sequence or series. Where we start with the first one, starting with k equals 1 or whatever, right? So if you start with k equals 1, this is very clear. Otherwise, it might be a bit muddy. So this is the nth partial sum, S sub n, is the cumulative sum of the first n terms of a sequence or a series. Okay, like an infinite series, starting with a sub 1. Now, finite series, we worked out the sum of a finite series here. So these things represent a series, but here we evaluate the sum of a finite series. You can think of this as evaluating the sum of a finite series. The idea of a series is more conceptual. It's like the idea of adding terms. This up here was a finite series. So for a finite series, you can evaluate the sum, and the result is typically a number in a basic problem. But finite series aren't as interesting as infinite series. Summation k equals 1 to infinity, a sub k, which is a sub 1 plus a sub 2 plus a sub 3 plus yada, yada, yada. The finite series above, okay, again, I just mentioned this, the nth partial sum. This is the nth partial sum of this infinite series. Imagine a sequence from a sub 1 on forever, a sub 1, a sub 2, a sub 3, with infinitely many terms, okay? Now, see, the idea of an infinite series is that it's the concept of taking these terms and adding them all up. A sub 1 plus a sub 2 plus a sub 3 plus da-da-da. It's an attempt to add infinitely many terms. But this infinite series may or may not actually have a sum. So when we talk about a series, we're basically representing a sum of terms. But actually, the sum itself may or may not exist. The series may or may not actually have a sum. By definition, a sum is a finite value. It's not infinity or negative infinity. And we're going to talk more about the idea of infinite series having a sum later. More in 9.3. Next up, we're going to talk about particular types of sequences and series. We're going to categorize them. Some very important ones.
Before we do that, here's a really great meme. I've had students really remember this. Students remember this. What's the joke? You have a lot of math writers on The Simpsons. What's the joke? In fact, many of you did this last week. I did too. Go ahead, say it. What does it say? You now know what this means, right? Yep, you got it. I ate some pie. I remember a student I had for pre-calc, and I saw a few semesters later, he wrote it on the glass walls. I think he was going a little wild because he was going nuts over a problem, but he wrote this on the glass walls. I ate some pie. You're going to remember this. I ate some pie. All right. They love math in The Simpsons. Okay. Very good. Now we're going to talk about particular types of sequences and series next.
Hi, everyone. So we're going to do section 9.2 on arithmetic sequences and partial sums. Well, what is an arithmetic sequence? Here's an example. By the way, it's pronounced arithmetic, not arithmetic. It's arithmetic as an adjective. All right, what's the next term in the sequence? You can think of a recursive relationship here. The next number in the sequence will be 14, because what are you doing to each term to get the next term? You're adding 3. So if I tell you right now, hey, to get your sequence, begin with 2, and then keep adding 3, then you get a sense of the sequence, right? Then in principle, you can get any term down the line. So an arithmetic sequence is determined by its initial term. Here it's a sub 1, although again, in other sequences, you might start with a sub 0 or whatever. Here, a sub 1 is 2. And also something called the common difference. That's basically the number that you keep adding over and over again. Here, it was 3. You keep adding 3 over and over again to get each new term. That's kind of a recursive way of looking at it. You take the current term, add 3 to get the next term. It's called the common difference, denoted by D. Now you might be going, why are you calling it a difference? Well, because we frame it as the new term minus the old term, right? The new term, 5, minus the old term, 2, is 3. So that's why we call this the common difference. Okay, here D is 3. Okay. It's a sub 2 minus a sub 1, or a sub 3 minus a sub 2, and so forth. Okay, so how can you get the common difference? For example, if these were like ugly fractions or something, and it wasn't obvious what was being added over and over again, then computationally, how can you figure out the common difference? Well, you could take the second term minus the first term, or the third term minus the second term, or the fourth term minus the third term, and so forth. The 1000th term minus the 999th term. And by definition, an arithmetic sequence has a common difference. This minus this, this minus this, this minus this. It's a common difference. It's the same number, in this case, 3. If you don't have a common difference, it's not arithmetic. All right. Sometimes one of these is easier. Depends on the numbers. So the following information completely determines our sequence. If I have a sequence and you care, then if I tell you the sequence is arithmetic, the initial term is a sub 1, which is 2, the common difference is 3, then you should be able to figure out, in principle, any term in the sequence. Although it may take some time. But what if I ask you for the 1000th term? Do you really want to sit there at your desk and go, okay, 2 plus 3 plus 3 plus 3 plus 3 plus 3? No, I don't think so. It's not worth it, even for a test grade. All right. So we're going to talk about that issue in just a moment. Again, I was mentioning the recursive definition, the idea that, okay, a sub 1 is usually given, not always, but a sub 1 is usually given. And to get the next term, you take the current term and add d, the common difference. Okay, where k is a positive integer. All right. The arithmetic sequence, 25, 20, 15, 10. This time you subtract 5, which means that the common difference is negative 5. So you can have an arithmetic sequence that's decreasing. That means that d, the common difference, is negative. For example, 20 minus 25 is negative 5. Okay, like I was saying before, what if I asked you to find the 1000th term in a sequence? You probably don't want to go 2 plus 3 plus 3 plus 3 plus 3. Okay, can we find a closed form formula, right? Not a non-recursive. I might phrase it this way on the test. A non-recursive closed form formula. Meaning that, for example, the 1000th term would not be defined in terms of the 999th term or the 998th term. It's going to be defined in terms of n. Okay. So here's the idea. Let's develop it step by step. Let's begin with a sub 1 and keep adding d until we get the general expression for a sub n. All right. The first term, a sub 1 equals a sub 1. A horse is a horse. Right? And then the second term, a sub 2, is the first term, a sub 1, plus d, the common difference. Before it was 3, right? 2 plus 3 is 5. To get the third term, well, it's true that you get the second term, but here's the idea. What's the third term? It's going to be the second term plus d. But what is the second term? It's the first term plus d. So if you substitute this in for this, you get a sub 1 plus d, that's what a sub 2 is, right? A sub 2 is a sub 1 plus d, all plus d. What's that? That's a sub 1 plus 2d. Likewise, a sub 4 is a sub 1 plus 3d. Now, this makes sense because the idea is that if you want to go from the first term to the fourth term, right? You want to go from the first term to the fourth term. How many times do you add the 3? Once, twice, 3 times. There was a song called 3 Times a Lady. Once, twice, 3 times a lady. All right. Another way to look at it. Let's say that you're climbing a ladder or a staircase. You're at the first floor of the ladder. All right. And then you want to get to the first floor of the ladder. The first step on the ladder or the first step on the staircase, right? And you want to get to the fourth step on the ladder or the fourth step on the staircase. Well, how many steps would you need to take if you're going step by step? 1, 2, 3. So to get from a sub 1 to a sub n, how many do you step? How many steps are there? Not n, but n minus 1. That's often an issue in computer science. Are we dealing with n or n minus 1? I did a professor who called it the fence post problem, right? If you have 3 fence posts, then you're trapping 2 regions in between, right? In general, to get the nth term, a sub n, you take the first term, a sub 1, and add d, how many times? Not n times, n minus 1. And remember, repeated addition is multiplication, right? For example, a sub 1 plus d, that's a sub 1 plus 2d. In general, if you're adding d n minus 1 times, you get this product. We're thinking again of multiplication as repeated addition. And that is the general nth term of an arithmetic sequence with initial term a sub 1 and common difference d. It's given by a sub n equals a sub 1 plus the quantity n minus 1 times d. In more advanced problems, you might not be given a sub 1. You might be given other terms or clues. then maybe you solve for a sub 1 at some point. Sometimes systems are involved. Right. Again, you take n minus 1 steps of size d in general to get from a sub 1 to a sub n. Here n is 4. You add d 3 times. Oh, and this is a discretization of a linear function. Okay, it's basically linear. This is linear in n. Remember, these are numbers. A sub 1 is a number, d is a number. This ends up being linear in n. So an arithmetic sequence will always correspond to dots on a straight line. Pretend that's a straight line. All right, example. Find the 100th term of the arithmetic sequence 2, 5, 8, 11, and so forth. That was the first sequence I showed you. Assume that 2 is the first term, meaning a sub 1. or I should say it starts with n equals 1. I should have said that, really. Well, I mean, if 2 is a sub 1, you're looking for a sub 100, right? Find a sub 100. 2 is a sub 1. Okay. So we can use our handy dandy formula because, okay, this is our formula, right? So we want to know the 100th term. Okay, so we plug in n equals 100, right? Because we want the 100th term, n equals 100. We know from before the common difference is 3. I mean, it's pretty straightforward here. You're adding 3 as your common difference to get each new term. So a sub 1 is 2. That's the first term. D is 3. I care about the 100th term. So we have a sub 100, n equals 100, right? Now again, if you didn't know this formula and you have your calculator in your hand and you love calculators, you could sit forever with your calculator. What could you do? You put 2 in your calculator and you keep adding 3. How many times? How many times do you add 3 to get the 100th term? If 2 is the first term. You add 3, not 100 times, but 99. My computer science professor called this the off by 1 bug, an OBOB, where in computer science, you often have to think, okay, am I dealing with n or n minus 1? Because these issues come about. You get 299. And of course, we follow the usual order of operations. The multiplication precedes the addition. And of course, any scientific calculator, more than a couple of bucks, would tell you that. All right, 299. You get it by taking 2 and adding 3 99 times. I think this is faster. You'll get the same result. Now, here I discuss the formula for the partial nth sum of an arithmetic sequence. Remember what this is. I'm going to pull back 9.1 because remember what this is. All right. S of n is this over here. Right? S of n is this thing over here. It's the sum of the first n terms, the cumulative sum of the first n terms of any general sequence or series. Okay, so in this case, if you know that you're dealing with an arithmetic sequence or an arithmetic series, then this is the formula for the sum of the first n terms, assuming you're starting with n equals 1. I will not require you to use this on homework or exams, but be aware that it's here. It makes sense. The sum of the first n terms is equal to the number of terms times the average of the first and last terms. That kind of makes sense. It's like n times the midpoint of the extreme terms. Yeah, the number of terms times the average of the first and last terms. And I have an example. Okay, the 100th term is 299, but if you add everything from 2 up through the 299, you get 15,050, and you can use the formula for that. Again, this won't be on your final. If I have time, I'll send you some cute videos on how the brilliant mathematician Carl Gauss figured this out. Add the first 100 positive integers. Gauss's teacher gave this to the class as busy work while the teacher did something else. But Gauss came up with a very clever way of doing it, and there are cute variations on that. And actually, bear in mind, this thing here, this is a finite arithmetic series, right? 1, 2, 3, and so forth. That's an arithmetic sequence. You can think of the positive integers as a positive sequence. And you're taking the 100th partial sum. Okay, next up, geometric sequences, partial sums, and series. Try to guess what we do here for geometric. And these are actually much more important than arithmetic in calculus, and we'll see why.
Before we go to that, I would like to show you some of these videos. And some of you will see more of a 9.4, by the way.
Hi, everyone. This is section 9.3 on geometric sequences, partial sums, and series. Now, with arithmetic sequences, we took the initial term, and then we kept adding the same number over and over again, the common difference. Take a wild guess what's happening here. Let's see, 2 to 6, 2 to 6, 6 to 18, 18 to 54. Here, we're multiplying by the same number over and over again. Here, 3, which is called the common ratio, not the common difference. Because 6 over 2 is 3, 18 over 6 is 3, and so forth. Here we begin with 2. After that, we successively multiply by 3 to obtain the other terms. Unlike for an arithmetic sequences where we added, here we're successively multiplying by 3. So a geometric sequence is determined by its initial term. We normally start with a sub 1, which is 2 here, right? Let's see here. Okay, so common ratio denoted by R. Okay, the second term divided by the first term, or the third term divided by the second term, and so forth. Here, R was 3. So again, you could either do 6 divided by 2, that's 3, 18 divided by 6, that's 3, 54 divided by 18, that's 3, and so forth. Now, here you might be going, oh, well, why would I need to do that? Bear in mind, these numbers could get very ugly. They can become ugly fractions. So it may not be obvious what the common ratio is just by looking here. You might have to actually have to work it out, like this over this, or this over this. We have a choice. And sometimes something like this over this might be easier than this over this. For example, maybe this thing is a hideous fraction. Okay. So the following information completely determines our sequence. The sequence is geometric. The initial term is a sub 1, which is 2. Common ratio R is 3. Then in principle, you can get any term in the sequence. But it might take a while, for now. The recursive definition, you start with a sub 1, usually, that's given. Not always, but often it's given. To get the next term, you take the current term, and you multiply by R, the common ratio. To get term number k plus 1, you take term number k, multiply by R. It's like dominoes, which we'll talk about later. Here's term k. Here's term k plus 1. To get from 1 to the next, multiply by R. By the way, we assume that these are non-zero for now. Otherwise, it gets kind of tricky, right? Because let's say you start with 4, right? Then it's 0, 0, 0, 0. Is that really geometric if R is 0? No, that's kind of weird. All right. So for example, this sequence here is completely defined by the fact it's geometric. A sub 1 is 2, R is 3. Okay, the formula for the general nth term of a geometric sequence. Let's start with, it's similar to what we did for the arithmetic, except here, instead of adding D step by step, we're multiplying by R. So we have A sub 1 equals A sub 1. Okay, A sub 2, how do we get that? It's A sub 1 times R. To get A sub 3, remember, A sub 3 is, by the recursive definition, A sub 2 times R. A sub 2 is A sub 1 times R. Plug this in for here. And you get A sub 1 times R, and then this guy is times R. So we get A sub 1 times R squared. A sub 1 times R squared. So to get from the first term to the nth term, you don't multiply by R n times, but n minus 1 times. Here, we multiply by R twice. To get the third term, we multiply by R twice. A sub 4 is A sub 1 times R cubed. Again, using my step analogy from before, if you're going from the first step of a ladder or staircase to the fourth step of a ladder or staircase, okay, how many steps do you actually take if you go step by step? Well, 1, 2, 3. Again, it's that computer science issue. You got to be careful. So in general, to get from the first term to the nth term, it's A sub n equals A sub 1 times R to the n minus 1, because you multiply by R n minus 1 times, and that's exponentiation. For example, here, R squared means that you multiply R times R, right? You multiply 2 copies of R. Again, the general nth term of a geometric sequence with initial term A sub 1 and common ratio R is given by this. Remember it or figure it out. Now, this represents a discretization of an exponential function. And notice we have n and an exponent here. If these are numbers, right, we consider these as basically constants or numbers that we find, right? We end up having an exponential function in n, okay? Maybe a discretization of that, right? A sequence. In fact, when we did the card charts example, remember Norma, the game show player on Card Sharks, when you had to turn 7 cards, right? And she won $28,800. We modeled it with a smooth J curve, but actually, technically, it was dots. It was a geometric sequence because, it's, flip a card, flip a card, flip a card. It's a discrete scenario, not a continuous scenario. By the way, there was a $200 bump in the middle, but we're ignoring that for now. Okay, this is like card charts. This is really the card charts situation, okay? It's not so much a smooth, continuous exponential function. It's more a discretization of that. It's really a geometric sequence, really. So if you say that the value of a house increases by 2% per year, and you're reassessing it every January 2nd, then you're really talking a geometric sequence. All right. So geometric sequences often arise from exponential models, like for compound interest, population growth, and unfortunately, coronavirus growth, right? If you want to track week by week, for example. Okay, example, find the 6th term of this geometric sequence. Although this you could do brute force, boom, 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 all right? I guess we could check our work that way. Assume that 2 is the first term, A sub 1. So we're given A sub 1, we have to find A sub 6. Okay. A sub 1 is 2, and what's the common ratio? All right, now, so here, this is an example. If I were to ask you what's the common ratio, you might go, wow, here, it's not as clear as before, but think clearly, think logically. You can go A sub 2 over A sub 1. What's that? It's going to be -1/2. Or perhaps even easier, look at this. A sub 3 over A sub 2, 1/2 over -1. Well, that's -1/2. That's even easier. So then here's our general nth term formula for a geometric sequence. We want the sixth term, so we plug in n equals 6. Right? We know that the first term is 2. We know the common ratio is -1/2, or we figured it out, right? To the 6 minus 1. Okay, so to the fifth. This power here is -1/32. Multiply in the 2, you get -1/16. Now, you don't have to check, but it might make us feel better if maybe brute force, right? Remember, this is the common ratio. What's 1/2 times -1/2? 1/2 times -1/2. It's -1/4. What's -1/4 times -1/2? -1/4 times -1/2 is +1/8. And lo and behold, what is 1/8 times -1/2? It's -1/16, which verifies what we had here. And certainly, if I ask you for the 100th term, then you're going to want to use this formula. Although, if I were to ask you for the 100th term, then you might want to leave exponents to your final answer because you could have very ugly pieces. Now, incidentally, as n approaches infinity, what do these terms seem to approach? If you keep going on and on and on, and you multiply by -1/2, what seems to be happening? They're approaching 0. They seem to be approaching 0, and they do. When does that happen? When do the terms of a geometric sequence or series approach 0? That happens if and only if R is strictly between -1 and +1. So if R is -1/2, like here, or +1/2, okay, or another way of putting it, the absolute value of R is less than 1. Okay, so these terms approach 0 if and only if the absolute value of R is less than 1. If R, the common ratio, is strictly between -1 and 1, like -1/2, +1/2, 0.99, -0.99, then the terms will approach 0. If R is 0.99, it might take a while for it to really get close to 0, but yes, it'll approach 0. Imagine that you have a store and it cuts prices 1% every week, right? Then eventually things will be very cheap. Okay. Now, don't worry about this. The formula for the nth partial sum of a geometric sequence, but it's the sum of the first n terms, basically. You don't have to know this formula. Now, you do have to understand the concept of an nth partial sum, the idea of adding the first n terms, the cumulative sum, but you don't have to know this particular formula. Oh, good. So we get to kind of skip over this stuff. Good. Oh, good. Look at this. All right. All right. Next up, this will be fascinating. And these are extremely important in Calc 2, Math 151, infinite geometric series. Okay. I mean, finite series aren't so interesting. And why didn't we care so much about infinite arithmetic series? We'll see next time.
Any questions before I go on? Because this is the gold mine. Okay. It really helps when you enter Calc 2 with this kind of knowledge. Any questions? Infinite geometric series. Here's the gold mine. All right. Questions in chat?
Hi, everyone. So infinite geometric series, this is crucial in Calculus 2. Now, in general, geometric or not, an infinite series converges by definition if it has a sum. And you have a sum if the partial sums approach a real number. And I'm going to explain this in a moment. It's when the partial sums approach a number. Using this limit notation, the partial sums, S sub n, in the long run, as n approaches infinity, if you consider the sum of the first 100 terms, first 1,000 terms, first 1,000,000 terms, okay, if these cumulative sums approach a number, S, okay, then that number S is the sum of the series, and therefore the series converges. If not, the series diverges. Okay, if there is no limit, right? If the partial sums don't approach a number, there is no sum, and the series diverges. Every series either converges or diverges. Every infinite series either converges or diverges. Converges means has a sum, diverges means no sum. Consider the geometric series that goes like this. Okay, so the partial sums look like this. And in fact, I have some good pictures for this. Oh, let me try to get these here. Where are the good pictures? There we go. Okay, I have a bunch of good pictures here. This one over here. Okay. 1/2 of the pi plus a quarter plus an eighth plus a 16th plus yeah. This isn't my work, by the way. All right. Well, it looks like we're approaching, as we add on more and more terms, the sum, the partial sums are like the total areas we're picking up cumulatively. 1/2 plus a quarter is 3/4, plus 1/8, you get 7/8, plus 1/16, you get 15/16. There's a pattern there. It looks like we're approaching 1, the whole pi, right? Even think in terms of squares and rectangles, right? The area of this rectangle is 1/2, plus the area of this square, I guess, is 1/4, plus the area here is 1/8, plus da 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 da. Okay, we're approaching filling in the whole square. No, at no finite time, at no finite value of n, is it true that we have a partial sum of 1, but the partial sums are approaching 1. Right? They're approaching 1. Okay, and later on we'll prove it using a formula. Okay, this series has a sum, it is 1. So if you plug these into your calculator and you add these all up, as you add in more terms, then the partial sums will be approaching 1. Okay, now, I guess I'll go back here. What is the common ratio here? The initial term was 1/2, but what's the common ratio? What do you multiply this by to get that? Actually, that is also a half. 1/2 times 1/2 is 1/4, 1/4 times 1/2 is 1/8, and so forth. So in this case, notice here, I forgot to make my point. R equals 1/2, and in this case, this geometric series converges because the value for R is crucial. By the way, let's assume a sub 1 is not 0. Okay, the value of R is absolutely crucial. This alone will tell you whether the geometric series converges or diverges. Assuming this is not 0, it doesn't even matter what this is. As long as this is any non-zero real number, right, then R is enough to tell you whether the whole series will converge or diverge. I mean, a sub 1 could have been 10 billion, right? If R is 1/2, you're going to get a sum. It'll be a huge sum, but there will be a sum. Okay. Now, the geometric series, we saw this before. We saw the sequence 2, 6, 18, 54. Let's consider the corresponding infinite geometric series. This has no sum. Look at the partial sums. 2, 8, 26, 80. I mean, these partial sums are approaching infinity. That means this has no sum. By definition, in order to have a sum, it would have to be finite, not infinite. Infinity does not count as a sum. All right, does not count. So this series does what? This geometric series diverges. It does not converge, therefore it diverges. And what's the key here? What was the common ratio again? R was 3. The multiplier to get from each term to the next term. Now, again, this series converged because R was 1/2. It was pretty close to 0, hint, hint. Here, R was not close to 0. It was 3. This series diverged, hint, hint. How about this here? Okay. The geometric series, this is a geometric series, 1 minus 1 plus 1 minus 1, and so forth. It's an alternating series. What are the partial sums? 1, 0, 1, 0. This reminds me of Bender's dream from Futurama. He was a robot. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, like binary, right? See, here's the thing. These partial sums, even though they're not blowing up towards infinity, they're not approaching a single number. They're alternating between 1 and 0. So this is not approaching a single number. So this series diverges, all right? But in a different way. This series diverges more by oscillation. Okay. We might say that this geometric series diverges to infinity because the partial sums approach infinity. Okay, over here, this series diverges by oscillation because these partial sums just kind of wobble between the same two numbers, right? But these don't approach a single number, and you can't say 1/2. Although some software programs try to pull that. They try to say these approach a half. I don't quite buy that. All right, this has no limit, right? S sub n does not approach a real number as n approaches infinity. This series diverges by oscillation. And what was the value for r? Hey, what do you multiply by to get each new term? You multiply by r equals -1. So for -1, you get kind of this weird behavior here. Divergence. So, and by the way, what happens if r equals +1? I don't know if I have an example like that, but what if we had 7 plus 7 plus 7 plus 7 plus 7 plus 7, and so forth? Here, the common ratio is 1, right? But wait, is this going to have, are the partial sums going to approach a finite number? See, 7, 14, 21, the multiples of 7 are not going to approach a number. You're going to diverge to infinity once again. So once again, this series diverges to infinity. And what was the common ratio? It was 1. All right. So notice that for r equals 1 and r equals -1, we diverge, right? But it's kind of a close call in these cases. If you're closer than 1 to 0, right? If you're at like 1/2 or -1/2, you converge. If you're more than 1 away from 0, you diverge. Bottom line, a geometric series converges if and only if r is strictly between -1 and 1. That is, the absolute value of r is less than 1. And by the way, this was equivalent to the notion that the terms of the corresponding geometric sequence, the actual terms in the sequence, approach 0, because this was also the same condition, right? R is strictly between -1 and 1. It was the same equivalent condition. So if r equals 1/2, converges. It's close enough to 0. If r equals 3, diverges. It's too far away from 0. If r is -1, you diverge. If r is 1, you diverge. Those are the borderline cases, but you do diverge at the borderline cases. These are strict inequalities. Now, this is called the harmonic series, the sum of the reciprocals of the positive integers, 1 plus 1/2 plus 1/3 plus 1/4. It's one of the most natural series that has the property that the terms approach 0, but this is not geometric. It's harmonic. It's called the harmonic series, but it's not geometric. So the rules I just told you about don't apply regarding common ratios. This has no common ratio, not geometric, no common ratio, right? But the terms do approach 0. Now here's the thing. This is the easiest series whose terms approach 0. The terms of the series approach 0, and yet the series diverges. The series diverges. The terms of the series approach 0, yet the series diverges. It's not enough for the terms to approach 0, okay? When does an infinite series have a sum? We have clean rules for geometric series, but otherwise, calculus 2, you have like 11 tests for convergence or divergence, and they often don't tell you what the sum even is, if there is a sum. Okay, it's a challenge just to know, does it converge or diverge, right? Okay, so this is the easiest series where the terms approach zero and yet diverges. If you have a fishbowl in outer space where there's still gravity, okay, okay, you can pour in 1 gallon of water. The next day, what is a day? Well, anyway, an Earth day. The next Earth day, we pour in a half gallon of water. Then the next day, 1/3 of a gallon of water. Regardless of how big that fishbowl is, the capacity could be 1 trillion gallons of water. Someday, could be a long time from now, the bowl is going to overflow. This diverges to infinity, but slowly. And why did we not care about infinite arithmetic sequences or series? I should have said series here, I'm sorry. No infinite arithmetic series has a sum. Okay, none of these guys will have a sum, right? There's no way that the partials will, for example, here, this will diverge to infinity. There's no way the partials will settle down. If the geometric series has a sum, here's the formula. S equals the initial term over 1 minus r. It's beautiful. And it works if the series converges, because by definition, that's the only time you have a real sum. I mean, if r equals 1, that's messed up anyway. Cool example. Before, if I told you to write 1/3 as a decimal, what would you say? Okay, it's 0.3333333, right? Or in other words, 0.3 bar, which indicates repetition. That's a repeating bar or vinculum. That's in grade school. Now, in calculus, you often do the inverse problem, like we did with partial fractions, right? The inverse problem. I give you a repeating decimal. You find the corresponding nice fraction, integer over integer. So this is a property of rational numbers, right? They can be written in either form. Well, this is a number that can be represented as the sum of an infinite geometric series. This is 0.81818181 da 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 da. You can think of it as what? 0.81 plus 0.0081. Line these up. Plus 0.000081. These do line up. These do line up. 0.81 plus 0.0081 plus 0.00081 and so forth. I guarantee you this geometric series has a sum, and the sum is this number. This series has a property that the initial term is 0.81. Why is it a geometric series, and what's the common ratio? What do you do to get from here to here? You move the decimal point 2 places to the left. If you take a decimal number and you take the decimal point 2 places to the left, what are you doing? You're dividing by 100, which means you're multiplying by what number? You're multiplying by 1/100th or 0.01. And that is R. R is a penny, is 0.01, which means, by the way, hey, that's close to 0. That means the series is going to converge. Okay, that R is certainly close to 0. All right, plug it into our handy dandy formula. S equals initial term 0.81 over 1 minus the penny. $1 minus a penny is 99 cents. Multiply top and bottom by 100 to clear the decimal points. 81 over 99. Divide top and bottom by 9. 9/11ths. Folks, get your calculators. 9 divided by 11. What do you see? You might get a 2 in there as a rounding thing, but there you go. The inverse problem. Pretty cool, huh? Summation notation, get practice on the homework, but the idea with summation notation is if you want to indicate a geometric series more generally, more abstractly, find the general nth term, or here the general kth term. We have that formula, the formula for the general kth term of a geometric, and stick on this operator, right? So these represent terms in the geometric sequence. Stick on this operator to get the series. Summation k equals 1 to infinity. in principle, you're taking all these terms and indicating the sum, adding them all up. And here we do have a sum. It's 9/11ths. Sometimes in calculus, you want to shift the index so that you start with 0 as the lower limit. And this cleans that up to an I. If you make the substitution, you make it look a little nicer. But I won't push you too hard on that in our class. But you will get used to that later. The idea of doing substitutions to manipulate the index, to make things look nicer. All right. Important stuff in calculus. It gets even cooler later, next time.
So we're done through 9.3. And as we end, it is 9:30, but as we end, I'm going to show you what some of these things look like, right? So okay, and let's set up here. All right, I'm going to grab the tablet, ye old tablet. All right. Okay. All right. All right, just about ready. Okay, here we go. All right. So let's see. All right. So 716C, let's start with that. Right, this one here. All right. Okay. Okay, so I don't believe I've done this before. So let me check this one out. All right, so 716C, 6C. All right. Okay, so 716C. So it looks like this one's well suited for the addition method. I know it's a nonlinear system, but the addition method might work fine here. So going red. Whoops. All right. Okay, so we have x squared plus y squared equals 1. X squared minus y squared equals 4. Okay, so if we add equals to equals, basically add the equations, we get 2x squared equals 5. X squared equals 5 halves. All right, so x equals plus or minus root 5 halves. So far, so good. All right. And just to give you a little hint, I'm going to check the solution, make sure we're on the right track here. Oh, okay. So I'm on the right track, but let's see what happens here. So we have x squared equals 5 halves. Actually, it wasn't even necessary for me to go to this step, because if you try to find y, right? So you have, for example, x squared plus y squared equals 1. Okay. Now I know that here we normally rationalize the denominator, but I mean, yeah, you can rationalize the denominator, but it turns out that won't matter. Okay, so this would end up being root 10 over 2, I think, but I don't think it's even going to matter. Because, okay, we have that x squared equals 5 halves. You don't even need this, okay? You don't even need to put this stuff over here. Because if you substitute 5 halves for x squared here, you get 5 halves plus y squared equals 1. Then you subtract 5 halves from both sides. You get y squared equals 2 halves minus 5 halves is negative 3 halves. Wait a minute. Y squared equals a negative number. Y squared equals a negative number. Is there any real value of y that'll satisfy this? Well, the answer is no, because squares of real values are never negative. Squares of real values are never negative. Put that in purple here. Squares of real values are never negative. We're dead meat. We cannot find a real value for y, right? Which means that the solution set will be the empty set. Because if you can't find a real value for y, you're dead, remember? Because our solutions here would have to be ordered pairs of real numbers. There's no real value of y that'll work. We're dead meat here. Any questions about that? Okay, any questions? I'll go ahead and say this is 716C. And there are different ways of approaching it, by the way. All right. And then 74H. Okay. Yeah. Okay. And that's fine. I can review. So let me see if I can grab that, those notes from my my marked up documents here. I do keep a record of the my notes from the office hours. Okay. So 7.42H. This one. Right. Okay. So let's this is a partial fractions one. So 742H in red. Again, it's my red color here. All right. So first of all, it's proper. It's third degree over fourth degree, right? It's third degree over fourth degree. So it's proper at least. We don't have to do long division, thankfully. Now down here we have repeated or powers of quadratics that are prime or irreducible over the reals. All right, we run up to the power. So, and by the way, it's in t, not x, remember. So our denominators go t squared plus 4, that's just to the first power, and then t squared plus 4 all squared. We run up to that power. And because these are powers of prime quadratics, right? Quadratics that are prime over the reals, we have linear forms on top. So it's at plus b. It's not ax plus b. It's at plus b. T is the variable here, right? And then on the top here, like ct plus d. Again, a linear form in t. Okay. Any questions thus far? Because I basically sketched out the initial parts of the solution in these office hour notes. Now, to get the basic equation, you have to multiply both sides by the LCD here, all right? The square of t squared plus 4. So you get the numerator on the left. Maybe I should write it out. You actually get the numerator on the left. So you get the So you get the 5t cubed minus t squared plus 20t minus 8. Okay, I'm going to go ahead and resave this. I'm doing a redo here. Okay, so that numerator equals, because when you multiply a fraction by its bottom, you get the numerator, equals, okay, you're multiplying both these fractions by the square of t squared plus 4, all right? So when you multiply this fraction by two of these guys, all right, it's kind of like this. I'll give you an example. Kind of like if you had x squared times 1 over x, what happens? Well, an x here would cancel out with an x here, but you still get an x over there. X squared divided by x is x, okay? Similarly over here, we have the top at plus b. When you multiply this fraction by this guy, all right, it's very similar to this, where you have two of these guys, okay, being multiplied on this fraction with one copy on the bottom. Okay, one of these guys will knock out that, but there's a second copy that survives out there, the t squared plus 4. Plus, when you multiply a fraction by its denominator, you get the top, ct plus d. So that's the basic equation. Were there any problems up to the basic equation?
No, not with the basic equation, but I just struggled after foiling it. I didn't know how to get the values of A, B, C, and D.
Okay, so let's make sure that the distribution is right. So again, it's the same left-hand side here, right? Equals, FOIL this, at times t squared is a t cubed, all right? Outer product, at times 4, 4a t. Inner product, bt squared. All right, b times 4, 4b. Plus ct plus d. All right. Now combining like terms. Okay, so I'll go and do this. Something times t cubed plus something times t squared plus something times t plus something. So what goes in the parentheses? Well, we have at cubed over here plus bt squared plus we have the 4at and the ct, so that's 4a plus c. Got to kind of squeeze it in here. Plus, and then what do we have here? We have the 4b and the d. All right. And on the left, we have, I'll do it like this. 5 times t cubed plus -1 times t squared. It's good to indicate what the coefficients are. And then write out the rest. All right. Plus something times t plus something. 5 times t cubed plus -1 times t squared plus 20 times t plus -8. So what's the system? Okay, we're going to match coefficients of t cubed. A equals 5. And there's going to be a big brace here. All right, A equals 5. Over here, B equals -1. 4a plus c equals 20. That might sound depressing, but wait a minute. A is 5. Hey, A is 5. So we have 4 times 5 plus c equals 20. Turns out c is 0. Kind of running out of space here, but c equals 0. And then 4b plus d equals -8. b is -1. -4 plus d equals -8. Add 4 to both sides. D equals -4. All right. So in green, we have a equals 5, b equals -1, c equals 0, and d equals -4. We're not done yet. We have to plug into the original form. So it's going to be 5t minus 1. Let's do it up here. Well, I should probably 5t minus 1 over the regular t squared plus 4 plus c is 0, d is -4. C is 0, d is -4. -4 over the square of t squared plus 4. And if you want to pop out that negative sign, that's fine. Okay, let's see here. 5t minus 1 over t squared plus 4 minus 4 over the square of t squared plus 4. Right. All right. Any questions about that? Any questions? Okay. If you made an error, do you see your error?
Yeah, I got it now. Thank you. I just was having trouble combining the like terms. I don't know why. I just wasn't doing it correctly.
Okay. Any questions? See, any questions? So this is okay here? Lots of work, I know. And I'm recording this, right? Thankfully, yes, yes. All right. So it'll be posted by midnight tonight. Okay,
I
so
have one.
let's do this. I'll return at 9:53. Okay.
Can you hear me? Hello.
And then if anyone has any questions by then, let's come back at 9:53. And let's see if there are any more questions. Oh, Nick, I can't hear you. Are you muted?
No. Hello. No, I'm not muted. Can you hear me? Hello.
Oh, okay. No, yeah, it was my fault. Yeah,
Oh,
I guess
you can hear
I
me?
was. Yeah, I guess I was muted.
I thought I was crazy.
So yeah, but I wonder what happened. So yeah, I guess I couldn't hear because my mute button was on for some reason. Okay.
Okay.
Yeah, okay, you're good now. Yeah, do you have any questions?
Well, I have one more. It's on 8.1, number 12, but I can't stay I can't stay around for too long. I got to go at like 10.
Okay,
So
but did you get this? Did you get this?
yeah, I got that. I was just having trouble with like combining the like terms, like the 4a plus c and then the 4b plus d. Like, I don't know why. I just like wasn't getting to that step. So, but once you showed that, I was easily able to solve it.
Okay, so and you said you go 8.1 what?
12.
Oh, okay. Now okay, so I could proceed with this. Shall I just proceed with this and see where you may have gotten stuck, or
Well, I was just saying that I have a question on that, but I have to go in like 10 minutes. So should we do it next class? There's no rush for it. It's the only one I haven't done in that chapter. So should I just wait for next class to ask it then?
perhaps have you attempted it?
Yeah, I did attempt it. I just kind of gave up after a while.
Well, let's. I mean, if you have time, we can try to get you started. And I can continue with this. So let's. Let me go. Let me go. Go back. Let's see here. Okay, let me get on our page here. All right. So. Okay. So let's use a different color. Let's use let's use purple. All right, so let's see. So let's start with the initial augmented matrix. And this is 8, 1, 12. All right, so 1, -2, -1 / 3, 5, -10, -5 / 11, 4, 3, 2, -18. Okay, so let's try to let me first quickly check this. All right, now we like the 1 up here. I'll come in blue. We like the 1 up here, but what do we want to turn these positions into?
Zeros.
Zeros. So let's eliminate down. All right. So so I'm just going ahead and proceeding with this. Okay, so the old row 2 is 5, -10, -5, 11. I want to add how much times row 1?
-5.
Right. -5 times 1 is -5. -5 times -2 is 10. -5 times -5 times 1 is -5. -5 times -2 is +10. -5 times -1 is +5. Oh, this is looking kind of weird here. Okay, so -5 times 3 is -15. This is no solution? Zero, 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 -4? Wait, that's no solution. Maybe this wasn't that long. No solution. Because you're getting this here, right? Which is basically corresponding to the equation 0 equals -4. That's junk. In order for this to have a solution, we have to live in a world where this can be true. That's not true. Therefore, there was no solution.
Okay. I must have just been doing math wrong because I didn't get that for some reason. So
You didn't get the throw?
yeah, I see why now.
Okay. Well, no, I can see it was easy to make a mechanical error. I mean, I just checked myself, right? It's easy to mess up signs. It turns out that this row's messed up because it's basically corresponding to that equation. This is exactly when you can short circuit the process and go, hey, the solution set's the empty set. I don't have to do any more work. You don't have to bother going to row echelon form. You're dead right here.
Okay.
Or more precise, or actually you're happy because you have an answer right now. That's one way of looking at it. Yeah.
Okay, thank you, Professor. That's it for me. Have a good night.
Okay, you're welcome. Good night. And were there any other any other questions at this time? And I'm not muted, right? Okay. Okay, thank you. Yes, yes. Any questions? Any questions? All right. Take care.